Welcome to Math with Malia. Today we are doing the enVision Algebra Topic 10 Lesson 1 about the square root function. And after today's lesson, you will be able to describe the key features of the square root function and apply it to a real-world scenario. Here in the Explore and Reason, there is this large sphere-shaped stone found in Costa Rica, and the great circle is around the widest part of the diameter of the sphere. So part A asks us to use the formula for surface area of a sphere and rewrite it in terms of the circumference. So how would we do that? Well, we have to remember what the circumference formula is. So if we remember, circumference is 2 times the radius times pi. And if we want to solve that equation for just the radius, we're going to divide both sides by 2 and pi. So the radius would be the same as the circumference divided by 2 times pi. And then if we substitute that into the surface area equation, we would see that the surface area would equal 4 times pi times c over 2 pi squared. Simplifying that equation further, we would end up with our equation being c squared over 4 times pi squared. I'll write it down here since the space is a little bit small. So then we would have it times c squared over 4 times pi squared, as we squared everything in the parentheses. And then we can see that the 4's will cancel, and one of the pi's will cancel, and that leaves us with surface area equal to c squared, or circumference squared, over pi. Part B, the circumferences of the great circles of spheres range in size from about 6 centimeters to 6 meters. Make a graph that represents circumference as a function of surface area. So if we're going to graph that, we would see that it would make a square root function. I'm just going to draw a rough sketch of it since I don't have my graphing calculator, but it would increase less and less. Okay? If surface area was our x-axis and circumference was our y-axis. So it looks similar to what a quadratic equation might look like if it was turned on its side, and we're going to look at that again a little bit later on the next couple of slides. So here we go, example 1, looking for key features of the square root function. So our parent function is shown here in the graph, and since it is a square root, to make the graph, it's a good idea to choose inputs that are perfect squares, because we can easily take the square root of a perfect square and get an integer that we can graph easily for the output. So that's what they did in the table. They chose inputs that were perfect squares and then applied the function rule, take the square root of the input, and got the output. And as you can see, the graph has a minimum at 0, 0, and it curves and is increasing as it moves to the right. The domain is restricted to x greater than or equal to 0, because we can't have a real square root as a negative number. If you take a square root of a number, we have to have only positive inputs. And since the square root of a number cannot be negative, we're thinking that the square root of x means the positive square root of x. So since the square root of a number cannot be negative, then the range is also greater than or equal to 0. And what I'd like to show students is, if I were to make the graph have an axis of symmetry, it would look very similar to a parabola turned on its side. But since we're talking about a square root function, I'm going to remind you of this vertical line test that we can do for functions. If I draw a vertical line through any point of the function, if that vertical line intercepts the graph in more than one place, it is not a function. So that is why we can only have positive output values for our square root function, because otherwise it does not fit the definition of a function. And you can notice that both the x and y intercepts are both at 0. And it's always increasing as we move to the right. So what would the graphs look like of these functions with slight changes? So if we remember our transformation rules from previous functions in earlier topics, we remember that if there is a negative in front of the function, that means it's the opposite. So it is reflected over the x-axis. So we can draw a rough sketch of what the graph would be for part A, that instead of being positive values, our square root function reflected over the x-axis would be like this. So now, what are the x-intercepts, the domain, and the range of this function? So the x-intercept is still going to be at 0. The y-intercept would still be at 0. The domain is still going to be all real numbers, positive or greater than equal to 0. So x has to be greater than or equal to 0, but what about the range? The range now, since it's reflected, the range is going to be anything less than or equal to 0. All right, let's look at part B. What would the graph look like now? As we look at the input, what is happening? We are dividing the input by 10. So we are making the input smaller. That means we're taking the square root of a smaller number. So if we were to graph that, it would still be above the x-axis because it's positive. And I didn't do maybe a very good job of that. If this were the parent function in green, and we can see that q of x does not increase as quickly as the parent function because we are taking the square root of a smaller number, so the output would be smaller. Okay, let's go through the intercepts. The x-intercept would still be at 0. The y-intercept would still be at 0. The domain would still be everything greater than or equal to 0. And the range is still going to be everything positive. Okay, so those are the key features of the square root function. Now let's look at transformations, and specifically translations of the square root function, where we are moving it left or right or up or down. So here is our new function, the square root of x plus 3. So if we remember our rules about transformations, if the change to the parent function happens outside of the parentheses, I could put imaginary parentheses around my input. So my change is happening to the whole function, or the change is happening to the output, since it is outside the parentheses. So this means if I'm changing the output, I'm changing along the y-axis. I'm going to be changing it vertically. So in this case, remembering our transformation rules, adding 3 to every output means I'm going to move the whole function up 3 units. And you can see that in the graph. Each input is the same, but the output is then shifted up 3 units. So this is a vertical translation of the parent function. Okay, and that's because we added a constant to the output, or the outside of the parentheses of the function. The domain is still going to be all positive real numbers, and the range is still going to be positive, but instead of starting at 0, look where our function starts. Now it starts 3 units up from 0. So 3 units up from the parent function. So now our range is going to be greater than or equal to 3 because every output, including the initial value, is shifted up 3 units. How about another translation? This time, notice where the change is happening. You could imagine the square root being a special kind of parentheses. So now, if I put imaginary parentheses around the input, I can see that there is a change to the input. So now I'm going to be changing along the x-axis. So this is going to be a horizontal translation. Okay, and if we remember our translation rules, if the change is happening to the input, it actually moves in the opposite direction. And why that is you can think of, if this were the starting point on my function, in order to get it to be where it would be on the parent function, I have to move it 3 units to the right, or I have to add 3 units to my translation to get it back to the parent function. So since I have to add 3 units to get it back to the parent function, that means it has to start 3 units to the left. And so that's why when we have a change to the input, the direction seems to be opposite, when really it's just adding 3 to get us back to the parent function. And these are the same rules that we saw with quadratic functions or absolute value functions or linear functions. All the translation rules are the same, applied to all the functions. So again, this is a horizontal translation of the parent function, the square root of x. We added a constant to the input, so the domain is still going to be greater than or equal to something, but instead of starting at 0, we now started 3 units to the left of 0, or starting at -3. So this time with horizontal translations, the domain has changed. The range does not change. It is still starting at 0 and including everything positive for the output. All right, let's take a look at the next example. Try it. How does each graph compare to the parent function? So we're just looking to describe what kind of translation happened or occurred. And I like to just draw arrows so I can show you which direction the graph would go. So as we're looking at the new function g of x, I can see that the change happens outside the parentheses. So I know that this is a vertical translation, which means it's going to go down 4 units. Looking at p of x, I can see that the change is happening inside the parentheses, or a change to the input. So I remember my rules that changes to the input are changed horizontally. So this is a horizontal translation, and I have to think in reverse. So this means I have to subtract 10 to get my function back to the parent function. So that means this is going to be shifted 10 units to the right. Okay, example 3, rate of change of the square root of function. So if we recall, we have done rate of change with other functions, quadratic functions, and we do rate of change with linear functions. And the same method is going to apply for square root functions. Okay, we're going to have an interval, and since our graph is curved, we can't find an accurate rate of change between 2 points because the rate of change is constantly different. If I were to draw a graph or plot a line for slope, it's different at every point along the graph. So that's why we do average rate of change with curved functions like quadratic functions or square root functions. So we're going to take 2 points on our graph and calculate the average slope, if you will, or rate of change between those 2 points. So I say slope because it's the same formula that we use to calculate slope. So the first thing we need to do is we need to evaluate the outputs for each of those interval endpoints. Okay, so I'm starting at x equals 0, and I'm going to x equals 0.3. That's my first interval range. So we need to evaluate f of 0. So we just plug in our input and we get an output of 0. And then we need to evaluate the other endpoint of the interval, 0.3. And f of 0.3 is approximately 0.548 because we took the square root of 0.3. And then we also have a second interval that we're going to look at. And since we already have 0.3 as our starting point, we can just evaluate the input for 0.6, the third endpoint, and we get approximately 0.775. So now we have the outputs. We have points that we can use our slope formula for to calculate average rate of change. So for the first interval, going from 0 to 0.3, remember slope or rate of change is, I'm going to write the formula here, the change in y, or y2 minus y1, over the change of x, or x2 minus x1. So we're looking at the second point minus the first point. And we remember in algebra that instead of saying y, we use output for functions. So f of x for our functions, we're going to use our second point, or f of 0.3, and subtract the first point, which is f of 0. And then we're going to take the second input, which is 0.3, and subtract the first input, which is 0. And we plug in our numbers that we just got from evaluating the functions, and we do the math, and we get approximately 1.83 for the average rate of change for the first interval, for that blue line. Then we can do the same for the second interval, again plugging in the second output and subtracting the first output, which in this case is 0.3. And then we take the second input and subtract the first input, which is 0.6 minus 0.3. We plug in our numbers, we do the math, and we get an average rate of change of 0.757 for the second interval. So as we look at those two, 1.83 is greater than 0.757. And if we look at the slope of those two lines, the slope of this blue line and the slope of this green line, we can see that the first interval with the blue line, it is a steeper line, which makes sense that it has a higher average rate of change than the second. So we can see that while the function is increasing, the rate of change is slowing down because the slope, or the approximate slope between 2 points, is getting less and less steep. Let's look at the try it section. For the function h of x equals the square root of 2 times x, find h of 8, h of 10, and h of 12, and then find the average rate of change. So we need to do a couple things, just like we did in that previous example. We need to first evaluate the outputs, and then we're going to use the slope formula to calculate the average rate of change between those points. Okay, so I'm going to do part A down here. So we're going to evaluate h of 8 by just substituting in our input into the function. So 2 times 8, which equals the square root of 16, and the square root of 16 is 4. Then I'm going to evaluate h of 10, substituting in our input. So 2 times 10 is the square root of 20, and we can get approximate values for that. It's approximately 4.47, and h of 12, substituting in again, 2 times 12 is the square root of 24, and another approximate value is 4.90. Okay. And then if I'm going to calculate the average rate of change between these intervals, so the first one I'm going to do is from 8 to 10. So I'm going to write out the formula first, and then we can substitute the numbers. So my second point is f of 10. My first point is, it's h of 10. Let's use h, since that's the function they gave us. Minus h of 8, my first point, okay, over my second input, which is 10, minus my first input, which is 8, the endpoints of our intervals. Substitute the numbers, so 4.47 minus 4 over 2, and that average rate of change is approximately, or it might actually give me an actual number, 0.235. So there's our first average rate of change for the first interval, and then we're going to do the same thing for the interval from 10 to 12. So now my second point is h of 12, and I'm going to subtract the first point, which is h of 10, over 12 minus 10. Plug in the numbers that we got from evaluating the inputs. 4.9 minus 4.47 over 2, and that is 0.215. As we compare these two average rates of change, we can see that as we move farther to the right, the rate of change is less. It's slowing down, or it's increasing less and less. We can see as we move towards 12, as we go from 8 to 12, our average rate of change is less. All right, let's move to an application problem. So we have two plans to consider to determine the speed of a theme park ride with a circular wall that spins. If you've been to a county fair or anything, I hope you've been on these rides. They're a lot of fun working with centripetal force. So it's trying to figure out which of these plans they would want so that they have a faster ride with a certain radius, a radius of 3 meters. Okay, so we have plan A represented in a graph, and we can see actually just from the graph, they tell us what the speed is. It's about 6 when the radius is 3. For plan B, however, we don't have a graph, but we do have an equation for the function, 5 times the square root of r. So can we figure out what the speed will be for plan B? Well, yes, we can. We can just evaluate the function when the radius is 3. And so that's what we have here. For plan B, we're just evaluating f of 3, plugging in 3 for r, and we get approximately 8.7. So 8.7 is greater than 6 meters per second. So if we use plan B, then that will have a faster speed when the radius is 3. Okay, so that one's pretty straightforward. We just had to evaluate a specific radius and compare the two speeds. All right, let's look at the try it. Again, we're going to be evaluating the function given a specific input, okay? And it says to round to the nearest 1,000. So here we have our input is 17 for both of them, but what's different in the functions? For part A, for v of x, we can see that we're taking the square root of x and then dividing by 10. Okay, so we have a number and then divide it by 10. For w of x, we're taking the input and making it smaller before we take the square root. So for part B, we're taking the square root of a smaller number. Okay, so let's see what happens when we do that. We just have to substitute our input into the function equation or the function rule. So instead of x, v of 17 would be the square root of 17 and then divided by 10. And that gives us 0.412. And evaluating w of 17, again, just substituting my input into the equation. So 17 divided by 10, I would do 17 divided by 10 and then take the square root. And that gives us 1.304, rounding to the 1,000th place. So that definitely changes our output, depending on if the change is happening inside in the input or the output, okay? So that brings us to the end of the lesson. Again, the translation rules are similar to all the other functions that we have done up to this point. Horizontal translations, vertical translations. So that brings us to the concept summary. Again, square root functions follow the same translation rules that we have seen with other functions. Whether that's translations horizontally or vertically, the rules will be the same. And we just have to be aware of the change in either the domain or the range. Let's go through the do you understand section. What key features are shared among the square root function and translations of the square root function? Well, we saw at the beginning that either the domain would stay the same if it was translated vertically, or if it was translated horizontally, then the range would stay the same. Number 2, explain why each function is or is not a translation of the square root function or the parent function. So let's look at part A. We have a change to the input, so that would mean we are horizontally translating the function, but then we have this number outside multiplying this whole function by 2. This, remember, we have called a scale factor before, so that would be a vertical stretch. It's not just a translation. There is also a vertical stretch to the function, which we didn't talk about yet in this lesson. For g of x, we can see that we do have a horizontal shift and we do have a vertical shift down 3, but those are both translations, so we have not stretched or compressed our function. Number 3, error analysis. These are great for checking your understanding to see if you can spot a mistake. So a student identified 6,12 and 9,27 as points on the graph or solutions to the function of square root of 3x. What error did the student make? So really what this means is if I substitute and evaluate f of 6, I should get 12. So if I plug in the square root of 3 times 6, I would get the square root of 18, and that's not going to be 12. Let's take a look at f of 9. If I evaluate that input, I should get 27. So I substitute 9 into my input. That would give me the square root of 27, which is not 27. So what is the mistake that the student made? Can you see it? What if we switch the input and the output? Sometimes that happens with students. We forget that the first coordinate is our x-coordinate and the second coordinate is our output or our y-coordinate. So what if we did f of 12 and plug that into the equation? Square root of 3 times 12 is the square root of 36, and that is 6, okay? And if I evaluated f of 27, anticipating that the student mistook 27 for the input instead of the output, and we substitute that in, the square root of 3 times 27, well, what is this 3 times 27? It is 81, and the square root of 81 would give us 9. So this student just switched the x and y values in the coordinates. Number 4, what is the domain of the square root of x plus 3? So let's think what's happened to this function. The change is happening inside the parentheses, so that is a horizontal translation, which means we would have to add 3 to the new function to get it to match up with the parent function. So that means our graph would have shifted 3 units to the left. If it's 3 units to the left, then our domain has shifted 3 units to the left. So our domain, instead of starting at 0, it would start at -3. Okay, the do you know how section. How does the graph of each function compare to the graph of f of x equals the square root of x, or the parent function? And I'm just going to use arrows as we evaluate the translation rules. For number 5, all right, -2. That is happening outside the parentheses. The change is happening to the output. So that means this is a vertical translation. That means we are shifting the graph down 2 units. Number 6, the change is happening inside the square root or with the input. So changes to the input are shifting the graph horizontally. And I have to remember I have to move in the opposite direction to get my new function to match up with the parent function. So in order to match up with the parent function, I would have to subtract 5. That means I have shifted the whole graph to the right 5 units. For p of x, it's just in a different place, but the change is happening outside of the parentheses, or change is happening to the output. So I have shifted the graph up. That is a positive 5. So I have shifted the graph up 5. And for q of x, again, it's just changing the order. It doesn't matter. The change is happening inside the parentheses. So this is a horizontal translation. And since it's a positive 7, that means I have shifted the graph 7 units to the left. For number 9, given the function, find the average rate of change to the nearest hundredth. Okay, so we're going to do a lot of work here again, where we are evaluating the endpoints of the interval and then calculating the average rate of change. Okay, so I'm going to do number 9 down here. So we need to evaluate f of 2 as my first point, and we need to evaluate f of 10 as the second endpoint of the interval. Okay, f of 2 is 2 plus 7, which is the square root of 9, which is 3. F of 10 is 10 plus 7, which is the square root of 17. And then if I just do the average rate of change, I'm going to do the second point, f of 10 minus the first point, f of 2, over 10 minus 2, change in my input. And I'm not going to evaluate, I'm not going to do a decimal for square root of 17 right now. I'm just going to round at the very end so I get a more accurate answer. Square root of 17 minus 3 over 8. And if we do our calculations, this will give us, rounded to the hundredth place, 0.14. Okay, for number 10, I'll do it in a different color up here. We're going to do the same process. Evaluate the endpoints of the interval. Evaluate f of negative 3. Evaluate f of 5. And then calculate the rate of change, which is f of 5 minus f of negative 3. Make sure you're subtracting that number. Whether or not f of negative 3 is positive or negative, you're going to subtract it. Over 5 minus the first input, which is negative 3. So we're subtracting a negative 3, which means we're actually adding. So I'm going to just set it up and let you finish evaluating the function. I should change these to g of x. I always do that. You could evaluate the function g of x and then calculate the rate of change. Okay, so your turn to practice. Let me know if this is helpful in the comments, and I hope you come back for more math help with Math with Malia.